Okay, so today we're going to be doing container with most water. So in this question, you're given an integer array heights, yeah, like this, and then where heights I represents the height of the ith bar. So you can see like a very clear correlation here. The first one has the height of 1, second bar is the height of 7, third one has the height of 2, and so on and so forth. You may choose any two bars to form a container. Return the maximum amount of water a container can store. So what this question is saying that given like a bunch of bars like this, you want to find the largest container that it can make. So in this case, it goes something like this. That's a container. This is also a container. This is a container. This is a container, and so on and so forth. So effectively, we just pick two bars to serve as our left and right walls of this container. And then, well, the bars in the middle don't matter. We calculate the size of this thing, and we want to maximize that size. So it's just asking for an area, right? So if you think about it, the size of a container is just the area, which will be the height times the width. How do you even get the height between two bars? If you notice here, no matter what kind of container we draw, the height of the container will always be equal to the smaller of the two walls, basically. And this one can only go as tall as this, which kind of makes sense. You know, if you have a super tall wall and the other wall is short, it doesn't really matter that this one's tall. You physically cannot fit any more water in here. And then as for the width, well, width is a bit more straightforward. The width is just the distance between this and this. So in other words, programmatically, we can say that the height is the minimum of the input array height. It's a bit confusing because the names are the same. Don't blame me. Of I, which is the left wall, and then height j, which is the right wall. And as for the width, it's simply the difference between I and j. And with that, we can grab the area, okay? So we figure out the basic formula for measuring the size or the area of the container. Now we want to find the largest area given this input. So what do we see when we look at this, right? If we want to maximize the height, then we want two really tall ones. It doesn't matter if only one of it is tall, we need both of them to be tall, right? But the thing is, because this thing is not sorted or anything, we don't really know exactly where the tall walls are located. And what about this one? If we want to maximize the width, then we want j to be as large as possible and I to be as small as possible, right? That's a little bit more within our control. It's not as random. So in the best case scenario, in order to maximize this thing, j has to be at the very end, right? And then we want it to be at the very beginning. Of course, just because the width is maximized doesn't necessarily mean we have the largest area, because that also depends on the height. So in order to maximize the height, we start by maximizing the width, and then we slowly move the two pointers inwards to find the two best walls at the best possible width. So what that looks like in an algorithm is one that goes something like this. So we initialize pointers I and pointers j to the beginning and the end of the list. And then we also need a variable. I'll call this best. And best is going to keep track of the biggest area that we have so far. So at first, it has nothing. Then we're going to calculate the area between I and j. So in this case, just plugging in values into the formula, we have 1 times, this is index 0, and this is index 7, and that'll give us 1 times 7. So total of 7. So if one wall is smaller than the other, then we will throw away the smaller wall and move this wall inwards. And then we're hoping that we'll get a taller wall, which we do in this case, but sometimes you don't. So the result of this is that we can always keep fishing for like a taller and taller wall, right? So for example, the height of this is 7, the height of this is 6. So then we would move this one inwards. And then we're hoping that maybe there's a taller, like a tall wall here or something like that, right? Because now we went from a height of 6 to a height of 7, right? And then we can throw this away, and then we're hoping that we get like an even taller wall, something like this. Then the height of the container will increase. Of course, as we keep moving inwards like this, the width's gonna go down. So we're hoping to find a height that's even better to offset this reduction in width, which will overall give us a larger area. So all in all, I think it's a pretty simple algorithm. I'm just gonna do a quick walkthrough just to showcase it. So between these two, I is smaller, so we'll move it here. So this is after calculating the area of 7, and then now I is at 1. The height here is 7, and the height here is 6. Then we want to calculate this area here, which will give us the minimum between these two is 6, and the width is 7 minus 1, 6. So 6 times 6, 36. That is our new best. And then once that's done, we'll try to fish for better height. Well, we know that, using our human eyes that there's no better height, but the computer doesn't know that. So we still have to scan. So j will go inside. We'll go to j equals 6 because j is smaller than I. And then we'll calculate this area, which will give us 3 times 5. So 15, that's not better. We'll move this once more to here, j equals 5. And then this gives us a height of 7. So now this will be our container. And if we calculate this, it's the minimum between this and this. So that's 7 times the width, which is 5 minus 1, so 4. So that'll give us 28. 28 is smaller than this, so this doesn't get updated. Now, this is the interesting part. What happens if the heights at both I and j are equal? How do we know which one to throw away? Does it even matter which one we throw away? If it doesn't matter, why? So originally, as I was solving this problem, I actually had an idea to peek to the element next to it to see which one is taller. So for example, in here, you can see that this is taller than this. So I'm going to move the I over here instead. But it turns out that it doesn't seem to matter. So let's have a look at why. So let's say initially we have an input of something like this. So the original best is going to be 2 multiplied by 3, so 6. And then if we're not using the peaking algorithm, and then we arbitrarily just move the I to shift to the right by 1. So this is going to go here, I equals 1 now. Let's have a look at what happens. So the area of this is, well, the height of, first of all, the height is going to be capped at 2, and then the width got smaller, so the width is 2 now. So the total area is going to be, what, 2 times 2, so it's 4. So it's not better than best. What if we did use the peaking algorithm, and then we specifically move j over here, because the next bar is taller? So let's see what happens. I'm going to move j here, j equals 2. And then the area, well, it's still capped at 2, isn't it? So it's still going to be capped at 2 times the width, which is still 2, and that's 4. So basically nothing has changed. So basically, if you think about it, for an inner container to be better than what we have so far, both of its bars need to be larger. Both the I and the j bars have to be larger than the original values. So the only way that happens is if you reach the state where I is here and j is here, and then, oh well, this is kind of a bad example because the area here is 5. But imagine if this was like, I don't know, like 20 or something, right? Then the area here would be 20, which is better. So long as either I or j is not better than what we had, or is the same as what we had, it will always be handicapped. So that's why it doesn't matter if I pick the taller bar to go to first, because both bars will have to move to a taller one. Like if this was 1, then the height of the new container will be capped at 1. So there's no hope of this inner container being better than what we have so far, right? So having covered that, let's start coding. So the first thing we want to do is to define our I and j. So we'll say I and j is equal to 0 and the length of heights minus 1. So we just initialize them to the beginning and the end of the list. After that, we're going to keep a variable called best at 0, which is going to be the area of the biggest container that we have so far. But since we haven't calculated anything, I'm just going to leave it at 0. And because it's 2 pointers, I'm going to do while I is less than j. And then I want to compute the area at these 2 pointers. So we're going to say that the area is equal to, as we established before, the minimum of the heights at I and heights at j. And then we're going to want to multiply that by the width. So multiply by j minus I. And once that's done, if the new area is better than what we have so far, then we'll update our best. So we're going to say best is equals to the maximum between area and best. And then we have to handle the incrementation, right? So in the case where the left side is smaller, if heights I is less than heights j, then I want to increment I by 1. Otherwise, if the right side is smaller than the left, then I want to decrement the right by 1, so j minus equal 1. And then in the else case, this is where both left and the right bar is equal. And as we've established before, it doesn't matter which one I shift up. So I'm just going to say that I'm going to move the left one arbitrarily. And then once we're done with that, we'll just return the best. And that's it. There you go. The time complexity of this is just O of n, my friends. Because we're just doing 2 pointers and then we're looping through each element just once. And for the space complexity, it's also O of 1 because we're not using any extra memory except for these variables, which are O of 1. Okay, bye.